Hello everyone. In this lecture I shall discuss the Green's theorem, which establishes the connection between the line integral and the double integral. Recalling the line integral, as you know, if you are given a vector point function f is f1 I cap plus f2 j cap plus f3 k cap, then the integral line integral over the path c is given by integral c f dr is integral a to b f1 dx plus ft dy, or you can write integral over c. This I can write integral over c f1 dx plus f2 dy plus f3 dz. Now if you write it in parametric representation, it will be integral ft dt, where t is a parameter and with some limit a to b, and we can find it. Okay, by the process we will find this limit a less than t, a less than t less than b, say. Right, looking into the particular case we can find the limit. Of course we have discussed in our previous lecture. Now if f is a plane curve and in two dimensions, suppose f is given by here f1i plus f2j, then this line integral c f dr is integral c f1 dx plus f2 dy. Now the moment c is a closed path enclosing a region R, right, c is a closed path which enclosed a region R, then this line integral, we can denote it, this integral with a symbol of this here to indicate the closed path. Then this, and now by Green's theorem, okay, here we apply the Green's theorem connecting these two. Here by Green's theorem, okay, we will able to write it. It is del f2 by del x, right. f2 is differentiated with respect to x, minus f1 is differentiated with respect to y, del f1 by del y, and it is double integral of this region. We have dy dx or dx dy, means suppose c is a closed path here, and this encloses the region and creates this region R. Okay, so this closed path produced this region R, right, this closed path produced this region R. So then we are in a position to connect the line integral, right, this line integral c, this can be connected as, and this is equal to this. So this line integral, right, we have here line integral, and this is our double integral. So this Green's theorem establishes the connection between the line integral and the double integral the moment this line integral is a closed curve which produced a closed region R. Okay, so let me to write the exact theorem for the Green's theorem, exact statement for the Green's theorem. So now before that, let me to introduce myself, Professor S.K. Paikray, Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Burla, Sambalpur, Odisha, India. Okay, so now let me to write the exact statement of the Green's theorem. Now coming to the exact statement of this Green's theorem, let R be a closed bounded region in xy plane whose boundary C consists of finitely many smooth curves. Let f1 and f2, right, let f1 and f2 here, this f2 be continuous, two functions that are continuous, okay, and its partial derivatives exist, means we need del f1 by del y, del f2 by del x. This partial derivative exists everywhere in some domain, means this line integral c, this c is a path which is a closed path, okay, and it forms a region, as I have told you, it forms a region here, then it forms a region here, then integral C everywhere in some domain containing R. Okay, then integral C f dr, the line integral over this closed path C is nothing but the double integral del f2 by del x, f2 with respect to x and f1 with respect to y, minus this dy dx. You may write dy by dx, or dx dy. That depends upon you looking into the diagram and the strip. Okay, now further if I want to write it, I can write it is curl f dot k cap. Okay, k cap dy dx, alternative way to write, and this integral is over r, alternative way to write it also. So now we should remember that this is my Green's theorem. This is my Green's theorem provided the path is closed. Now if you solve some examples, then your idea will clear. Coming to the examples, example 1, verify Green's theorem. Given that your f is equal to y square minus 7y and 2xy plus 2x, and C is a circle in counterclockwise sense. C is x square plus y square is equal to here 1. Okay, it is given like this. Now coming to the solution here, you see, so here C is a closed path here, right? It is a circle, center at 0 and radius 1. So since this is a closed path, okay, so we will able to apply the Green's theorem here, right? C is a closed path here, and this produce the region here, right? This produce the region here. So we can apply the Green's theorem here. Now if we evaluate the line integral, integral C f dr, right? So it is a circle. You put parametric representation of C. Here put x is equal to r cos t, y is equal to r sin t. Since this is a complete rotation here, so 0 is less than t is less than 2 pi, right? So what is your dr? So r is you put here 1, this radius is 1 here, so your 1 cos t, simply cos t and simply sin t. So r is equal to cos t I cap plus sin t j cap. So what is your dr? Dr is derivative of cos t minus sin t I cap, derivative of sin t is cos t j cap dt. So this is your dt. Dr is this dt. Now integral C f so now here f dot dr is this multiplied this, now I with I and j with j. Okay, so this is multiplied, this is sin square, it integral 0 to 2 pi, it is sin qt minus, and it is minus plus 7 sin square t plus this 2 sin t cos square t, 2 sin t cos square t and plus 2 cos square t dt. Okay, and we evaluate this integral. If we evaluate this integral, then it will give you 9 pi. Okay, now if we want to apply the Green's theorem, if we want to evaluate the apply the Green's theorem, means we check the double integral. We check the double integral here. The double integral here is so this is the region, right? This is the region. So now this, if I take this first quadrant, then 4 will be multiplied this first quadrant here. It is y is equal to 1 minus x square root over, right, and it is my y is equal to 0, and for your x it is your 0, 2, it is your 1. So 0 less than x less than 1, 0 less than y less than 1 minus x square root over. So by double integral, your integral over the region R, right, it is fxy, it is del f2 by del x minus del f1 by del y, okay, it is dy dx. So del f2 by del x will be here, del f2 by del x is, this is with respect to x, okay, 2y plus 2, it is your double integral 2y plus 2 minus 2y plus 7, okay, dy dx, and the limit of y is 0 to 1 minus x square root over, and it is your 0 to 1 x limit, okay. If we evaluate this integral, this 2y cancel, so this is equal to 0 to 1, 0 to 1 minus x square root over, it is 9 dy dx, or I can write it, it is 9 into double integral dy dx, right. So this is nothing but 9 into, this is my nothing but the area of the circle, so this is equal to 9 into pi into 1 square, so 9 pi, okay. So this is your 9 pi. Actually we can have our details of our work, we can evaluate it, or you can change to Jacobian also, we can evaluate it, okay. F r theta Jacobian dr d theta, you can refer to the my lecture of your double integral, okay. You can change the order, but without integrating we can write it, okay. So you see the Green's theorem, how it is easy, okay. This Green's theorem, suppose the same question if it is asked, use Green's theorem to evaluate this. The alternative question is, alternatively suppose it is asked, one example it is asked, use Green's theorem to evaluate integral c f dr, where f is given here, so f is equal to your y square minus 7y comma 2xy plus 2x, and c is the circle x square plus y square is equal to 1 in counterclockwise sense. Then what will be the solution here? So here we simply write integral c f dr is del f2 by del x minus del f1 by del y dx dy, double integral over the region R. So this is by Green's theorem, and we will write it. So this is double integral, it is 9 dy by dx. So I write it simply 9 double integral dy by dx. So I simply write 9 into area of the circle. So I write it simply 9 into pi into 1 square, r square, so 9 pi, okay. So if it is asked that evaluate by using Green's theorem, we evaluate. If it is asked verify the Green's theorem, so in this previous example we have seen, so this 9 pi is equal to 9 pi, so therefore we write just one line, integral c f dr is integral over r del f2 by del x minus del f1 by del y dx dy. So therefore Green's theorem is verified. Thus Green's theorem is verified. Okay. So let us solve one more problem. Now coming to one more example, you are asked to verify the Green's theorem, okay. So now coming to the solution, we have by Green's theorem line integral c f dr is double integral over the region R del f2 by del x minus del f1 by del y dx dy, okay. And the region here is and the region here is a rectangle. It is 0 0, it is 2 0, 2 0. Now it is here 2 3, and it is here 0 3. So this is the rectangle here, and it is given in anti-clockwise direction. And the region formed by this rectangle, this is the region. So we can apply the Green's theorem here, because the region is closed here, right? So if we evaluate it, this we have double integral over the region R, del f2 by del x minus del f1 by del y, dy dx or dx dy is equal to, you can write, if I write dy, the limit of y is 0 to 3, 0 to 3 means it is my, here y is equal to 0 to y is equal to 3, this vertical strip I am taking, right? This vertical strip I am taking. For horizontally it slides from 0 to 2, 0 to 2. Here del f2 by del x, it is partial derivative of e to the power x, y square e to the power x, minus x square e to the power y, here dy dx. Okay, so that is equal to, you will write integral 0 to 2, and if you integrate it with respect to your y, treating x is equal to constant here, it is here e to the power x constant, it is y cube by 3, right? The limit is 0 to 3, minus x square constant, integration of e to the power y is e to the power y from 0 to 3, and it is dx. Okay, so this is equal to integral 0 to 2, it is e to the power x into, it is my 27 by 3 9, minus x square, and the integration of this is e cube minus 1, right? This is dx. Now we integrate with respect to dx x, so this will be my 9 e to the power x minus e cube minus 1 x cube by 3, here 0 to 2. So this will be substituting the limit, it is 9 into e to the power 2 minus 1, minus it will be here 8 by 3 e cube minus 1. So this is my answer in view of the double integral. Now if you think of the line integral, evaluation of the line integral, okay, if you think of here integral C f dr, it can be viewed as the sum of the 4 paths here, integral over C1, then integral over C2, it is over C1, then it is over C2, then it is over C3, it is over C4. Okay, you evaluate the line integral over these 4 paths. So it will be integral, this will be integral over C1 plus integral over C2 plus integral over C3 plus integral over C4, here f dr. Okay, so now individually we evaluate this and this. Let it be my I1 plus I2 plus I3 plus I4 say. Okay, so now you individually evaluate it. So for I1, integral over C1 f dr. For I1, here this path, in this path, here x is equal to, this is x axis, y equal to 0. So here y is equal to 0 implies dy is equal to 0. You put x is equal to t. So therefore what is your r? Here r is xi plus yj. So xi plus yj, x is 0i plus yj, and here y here is, and here y here is this. So means y is t square j, and the limit is 0 less than t less than 2. You see here the x varies from 0 to 2, right? So if we, therefore what happens to your I1? So your I1 is equal to integral 0 to 2, okay, it is t square j f. What is your f? F will be here y is equal to 0, so dy is equal to 0, so this term will vanish, right? So let me write is x square e to the power y. So this is my integral C x square e to the power y dx plus y square e to the power x dy. Okay, so I can write it integral 0 to 2 x square e to the power y. This dy term will here 0, so this will my 0. Okay, now x is my t, it is t square, here e to the power y is 1 t square dt. So now if you integrate it, it is t cube by 3 0 to 2 is equal to here 8 by 3. Likewise here integral c to I2 is equal to here f dr, integral c to f dr, right? So you will evaluate it. Here you put, so this is the line here this line is given by parallel to y axis, x is equal to 2. This line is parallel to x axis, it is x y is equal to 3, and this is here x is equal to 0, right, in that way. So here x is equal to 2, implies dx is equal to 0. Put y is equal to t. Okay, so what is here r? Now r is xi, means 2i plus yj tj. What is the limit? So the limit of y here, so y varies from 0 to 3. So it is y varies from 0 to 3, 0 less than y less than 3. Okay, so now here I2 is equal to integral c f dr. So this is equal to integral c, you see here x is equal to 2, y dx is 0, means this first term will vanish, and in second term it is x square e to the power y dx plus y square e to the power x dy, right? Means here y is equal to t, dx is 0, this will vanish here. So this is equal to here y is t, integral 0 to 3, means this is my t here, y is t, 0 to 3, y square, so y square is t square, and it is here e to the power 2 dt. Okay, so this is equal to e to the power 2 t cube by 3 0 to 3. So this is equal to 9 square. Accordingly you evaluate integral c I3 is equal to integral c f dr. So in I3 here y is equal to 3, implies dy is equal to 0. What is your r? R is equal to xi, so put x is equal to t, xi plus yj, so this is ti plus 0j. Accordingly you evaluate it. Your I3 will be integral c f dr. After the evaluation of I3, it will give you minus 8 by 3 eq, and coming to here I4 is equal to integral over c4 f dr. So here x is equal to 0, implies dx is equal to 0. Put y is equal to t, so therefore r is equal to 0i plus tj. Okay, now if you evaluate this integral, I4 is integral c4 f dr, so it will be integral 2 to 0, is not it? You see the path here is here it is here 3 to 0, it is here 3 to 0. Okay, 3 to 0, so it is here 3 to 0, 0 less than y less than 3 less than y less than 0, so this is t here. Okay, so this is f dr will be here t square eqi plus 0j into I plus the dr is 0 plus 1j, 0i plus 1 second, it will 0 plus t square dt. Okay, so it is t cube by 3 0, so it is here minus 9. So what is your I? So I is equal to I1 plus I2 plus I3 plus I4, right? And if you add them, you will get 9 into e square minus 1 minus 8 by 3 into EQ minus 1. Okay, so this is your. Now you see, in both cases you are getting the same result. Now in both cases you are getting the same result. Now the same question, if it is asked, use Green's theorem to evaluate, then this question is quite easy, no need to verify. Okay, usually it is asked, use Green's theorem to verify. So now if alternatively, usually the questions are asked like this instead of being verifying. So coming to the solution, by Green's theorem, integral C f dr is double integral over the region del f2 by del x minus del f1 by del y dy dx. Okay, so that is equal to, you write integral 0 to 2 integral 0 to 3 y square e to the power x minus x square e to the power y dy dx, as I have already evaluated, and this will give you 9 into e square minus 1 minus 8 by 3 into EQ minus 1. This is your answer. Is it that not easy? Now coming to the applications of Green's theorem. Now coming to the applications of the Green's theorem, we have application 1, the area bounded by a closed curve C, creating a region R is given by, here area A is nothing but double integral over the region dy dx here. So this is half integral over C x dy minus y dx, So now coming to the proof of this discussion here. You have by Green's theorem, here double integral del f2 by del x minus del f1 by del y dy dx is equal to line integral over C f1 dx plus f2 dy. This is by Green's theorem. Now if I put for f1 is equal to 0 and f2 is equal to x, so this will be here double integral over R del f2 by del x minus del f1 by del y. It becomes here del f2 by del x is 1 dy dx. So this is equal to simply here del f1 by del y will be here 0. So this is simply double integral dy dx over the region, and in view of this we are getting this. Now in view of this we are getting, this is integral C f1 is 0, so 0 dx minus f2 is x dy, right? Let it be my equation star. Again for f1 is equal to minus y and f2 is equal to 0, what I am getting? Double integral over R del f2 by del x minus del f1 by del y dy dx is equal to, so del f2 by del x is 0, del f1 by del y is here 1, so it is minus of minus 1 only. So integral over R dy dx is, I am getting here, it is integral over C f1 dx plus f2 dy. This is your f1 dx means this x dx, and here it will be f2 d f1, so this will be your minus y dx. Let it be my equation double star. If I add star and double star, okay, adding star and double star, so this is my area A, this is my area A, is not it? So twice A is equal to integral C x dy minus y dx. So what is your A? This implies your A is equal to integral C, half is divided here, x2 is divided, so this is x dy minus y dx. So this is the area, right? If I think of one application, coming to an example, so now coming to this example, you are asked to find the area of the ellipse, area bounded by the ellipse. Okay, so here it is y is equal to b by a s x square minus x square root over. Okay, it is y is equal to 0 here. So your area of the ellipse is double integral over the region R dy dx is equal to integral from your y is equal to 0 to y is equal to b by a s square minus x square root over, right? And it is here. So if you think of this ellipse like this, okay, ellipse like this here, so this is the vertical strip here, this is y is equal to 0, this is y is equal to your b by a root over of s square minus x square. So now if I consider this area here, I have to multiply 4 times, okay, and this is my a and this is my 0. So this is 0 to a 4 times this, okay. And if we evaluate this integral, it will give you pi ab. Now in the sense of this integral, in the sense of this, but here to what we are putting, x is equal to a cos theta, y is equal to b sin theta, then this will satisfy x square by a square plus y square by b square is equal to 1. So I can write here area is equal to half integral c x dy minus y dx. Okay, so this is half integral c. So this is a complete rotation here. So this is 0 to 2 pi. Here x is a cos theta. Okay, x is a cos theta, and dy will be accordingly b sin theta d theta. It will be dy is b cos theta, so it will be ab cos square theta plus sin square theta, right, sin square theta d theta. So this will be your half ab, right, it is simply d theta 0 to 2 pi. So this is half, this is ab to 2 pi. So now this 2 and 2 cancelled, it is pi ab. So you see it is easy here, right? You see it is easy here, right? So likewise, as I have told you in the previous examples, applying Green's theorem, okay, suppose you are asked to evaluate this integral, use Green's theorem to simply ask that use Green's theorem to evaluate this, right? Evaluate the line integral. Then the line integral is difficult, but using Green's theorem it is easy. Now coming to the second application. Now coming to another applications, the area of a plane region in polar coordinate is half r square d theta. Okay. Now if you discuss it, coming to the discussion, you put x is equal to r cos theta and y is equal to r sin theta, because we are changing to polar coordinate. As we know, what is your area? Area is your dy dx. By the previous application, it is half line integral c x dy minus y dx. So this is half into integral c. X is your r cos theta, and what is your dy? Dy is r cos theta, so it is r square cos square theta plus sin square theta d theta. So this will be my half integral c sin square theta plus cos square theta is 1 half r square d theta. So this is what our area in this case. Okay. Now coming to one example, suppose you are asked, find the area bounded by the card yard. Find the area bounded by the cardioid. Actually, this equation of the cardioid here is r is equal to a into 1 minus cos theta, and the limit is given here 0 less than theta less than 2 pi, complete rotation here. So coming to the solution here, so we can apply this formula here. Area is half r square d theta. So here the area is half integral c r square d theta. So this is equal to half 0 to 2 pi here r square d theta. So the value of r is, this is half 0 to 2 pi here a square into 1 minus cos theta whole square d theta, and you evaluate this integral, it will 3 pi by 2 a square. This is the answer. Now coming to one more application. Now coming to another important application, transformation of the double integral of the Laplacian. Suppose coming to the discussion, let wxy be a continuous function, right, and your normal derivative here, this normal derivative is del w by del n. Okay, so now it is asked line integral c del w by del n ds, s is the arc length, is double integral del square w dy dx over the region. So this del square w actually it is your Laplacian. What does it mean? It means wxx plus wyy plus wzz. Okay, so let us solve one example, right? So this as per this application, the line integral of the normal derivative, this is normal derivative del w by del n, is nothing but double integral of the Laplacian. Okay, so let us solve one example. Now coming to one example, you are asked to evaluate line integral del w by del n ds, where w is this and r is the rectangle here, 0 to 2 and 0 to 1. Okay, so here r is the rectangle here, in x-axis it is 0 to 2 and it is y-axis it is 0 to 1, 0 to 2, 0 0 it is 2 0, it is 0 1 in y-axis. So this is 0 to 2, 0 less than x less than 2, and for your y it is 0 to 1, 0 less than y less than 1. So now it is asked to evaluate del w by del n ds. Okay, you know this is double integral over the region r del square w dy dx. So what is my del square w here? It is wxx plus wyy. So partial derivative of this twice with respect to x, e to the power x is e to the power x, again e to the power x, this is e to the power x plus e to the power y. So that is equal to, we can write here the limit of integration here is 0 to 2, 0 to 1 dx first, because I am taking x limit here, then dy, and it is my del square w is this del square w, you get it e to the power x plus e to the power y, e to the power x plus e to the power y. Now if you evaluate this integral, so this will be integral 0 to 1. Now evaluating with respect to x, my y is equal to constant here, so it is e to the power x y 0 to 2 plus e to the power, so this is with respect to x, means e to the power x integral is e to the power x, the limit is 0 to 2 plus e to the power y is constant, integration of dx is x 0 to 2 and it is whole dy. So is equal to, you will write integral 0 to 1, it is e to the power 2 minus 1 plus e to the power 2 e to the power y, 2 e to the power y, it is your dy. So now if I evaluate this integral, it will be here 0 to 1, it will be this is a constant here, e to the power 2 minus 1, and the evaluation of dy is y 0 to 1 plus 2 e to the power y, integration is e to the power y, and from 0 to 1. So this is equal to e square minus 1 into 1 plus 2 into e minus 1. Okay, so this is equal to e square minus 1 plus 2 into e minus 1. If I simplify, it is e minus 1 into e plus 1 plus 2 into e minus 1. So this is equal to e minus 1 taken common. It is e plus 1 plus 2. So this is equal to e minus 1 into e plus 3. So this is my answer. So now to conclude, the line integral, this Green's theorem establishes the link between the line integral and the double integral. Sometimes the line integral is quite lengthy. It may be the sum over the curve C1 plus C2 plus C3 plus C4. But by using Green's theorem, within no time we evaluate the integral. So Green's theorem minimize our effort to evaluate the integral. And further we have these applications, 3 applications as we see. So you should solve these examples carefully. In addition, you should solve some more problems from any standard book. Okay. Now with this, my appeal to all of you, if you feel that this lecture is helpful and interesting, please like and subscribe to this channel, which will boost my motivation to upload subsequent lectures for your benefit. So let us close this lecture. Thank you all.